Good evening. On this channel, I guide you to stars and other interesting objects nearby in our galaxy. I'm an AI voice, just so you know, but I hope you like me anyway. In this episode, we will be journeying to Luhman 16, a relatively recent addition to our understanding of the solar neighborhood. Luhman 16 is a binary system of brown dwarfs located in the southern constellation of Vela at a distance of 6.51 light-years from the Sun. These two brown dwarfs, Luhman 16a and Luhman 16b, form the closest known brown dwarf system to Earth and are the third closest star system overall, after the Alpha Centauri system and Barnard's star. Luhman 16 is located in the southern celestial hemisphere, relatively close to and east of Alpha Centauri in the sky. The constellation of Vela is next to the constellation of Centaurus. A more exact reference for Luhman 16 is Mu Velorum, a star in the constellation of Vela that would be positioned right above Luhman 16 if it was visible to the naked eye. The discovery of Luhman 16 in 2013 was made possible by the Wide Field Infrared Survey Explorer, or WISE. This infrared space telescope allowed astronomers to detect these cool, faint objects that would otherwise be invisible to the naked eye. The star system was discovered by Kevin Luhman, an astronomer at Pennsylvania State University, who was utilizing data collected by the WISE satellite. WISE was launched in 2009 and conducted a comprehensive survey of the sky in infrared wavelengths from December 2009 to February 2011. The mission was designed to identify objects that emit most of their light in the infrared part of the spectrum, such as asteroids, distant galaxies, and, importantly for our destination, brown dwarfs. Before the discovery of Luhman 16, the closest known brown dwarfs were located much farther away, and the third closest stellar system to the Sun was Wolf 359, a faint red dwarf star about 7.8 light-years away. The discovery of Luhman 16 and WISE 08550714, another sub-brown dwarf discovered by Luhman and announced in 2014, pushed Wolf 359 to fifth place and underscored the fact that even in the relatively nearby regions of our galaxy, there are still significant discoveries to be made. Luhman 16's proximity to Earth makes it a key object of study for astronomers seeking to understand the nature of brown dwarfs, as well as the broader structure and composition of our galactic neighborhood. The system was named Luhman 16 in honor of its discoverer, and the two components of the system were designated Luhman 16a and Luhman 16b. These objects are also known by their catalog name, WISE J104915, 57531-906, 1, which reflects their precise position in the sky. However, the simpler name, Luhman 16, has gained popularity due to its ease of use and memorability. The discovery of Luhman 16 was a significant milestone, not just because of its proximity, but also because it highlighted the importance of infrared astronomy in detecting faint, cool objects that are otherwise invisible in optical wavelengths. Brown dwarfs, which are objects that are too massive to be considered planets, but not massive enough to sustain hydrogen fusion like true stars, emit most of their light in the infrared part of the spectrum. This makes them difficult to detect with traditional telescopes that observe invisible light. WISE was specifically designed to survey the entire sky in infrared, which allowed it to detect objects like Luhman 16. The discovery was made by comparing images taken by WISE at different times, looking for objects that exhibited high proper motion, meaning they moved significantly across the sky relative to the background stars. This method is particularly effective for identifying nearby objects because their apparent motion is more pronounced compared to distant stars. Luhman 16's discovery also emphasizes the significance of systematic sky surveys in modern astronomy. Sky surveys like WISE, the Sloan Digital Sky Survey, SDSS, and the Gaia mission provide astronomers with a wealth of data that can be mined for new discoveries, often revealing objects that had previously gone unnoticed. Luhman 16a and Luhman 16b are both classified as brown dwarfs, with spectral types of L7, 5 and T0, 5 respectively. These spectral types place them near the boundary between L-type and T-type brown dwarfs. L-type brown dwarfs are characterized by their relatively warm temperatures and red colors, while T-type brown dwarfs are cooler and exhibit methane absorption in their atmospheres, which gives them a more bluish hue. The masses of Luhman 16A and 16B are estimated to be 35.4 and 29.4 times that of Jupiter, respectively. These masses are below the threshold required for hydrogen fusion, which is why these objects are classified as brown dwarfs rather than true stars. Brown dwarfs occupy an intermediate position between the largest planets and the smallest stars, and they are often referred to as failed stars because they lack the mass needed to ignite hydrogen fusion in their cores. The surface temperatures of Luhman 16A and 16B are estimated to be between 1,200 and 1,400 Kelvin, much cooler than the Sun's surface temperature of about 5,778 Kelvin. Because of their low temperatures, Luhman 16A and 16B emit most of their radiation in the infrared, making them very faint in visible light. In fact, these objects are so faint that they are invisible to the naked eye, even though they are only 6.51 light-years away. The atmospheres of Luhman 16A and 16B are rich in molecular hydrogen, methane, and possibly water vapor. The presence of methane in particular is a defining characteristic of T-type brown dwarfs like Luhman 16B. Methane is a molecule that forms at relatively low temperatures, and its presence indicates that the atmosphere of Luhman 16B is cool enough for methane to remain stable. This is in contrast to Luhman 16A, which, being warmer, exhibits less methane and more complex molecules like carbon monoxide. One of the most intriguing aspects of Luhman 16, particularly Luhman 16B, is its atmospheric variability. Observations have shown that Luhman 16B exhibits significant changes in brightness over time, a phenomenon that is likely caused by patchy clouds in its atmosphere. These clouds are thought to be composed of silicate particles and other minerals, which condense out of the brown dwarf's atmosphere at high altitudes. In 2013, observations using the European Southern Observatory's Very Large Telescope, VLT, revealed that Luhman 16B has a large dark region at its middle latitudes, a bright area near its upper pole, and mottled illumination elsewhere. This uneven illumination suggests that the atmosphere of Luhman 16B is dynamic and complex, with cloud patterns that change on relatively short timescales. The variability in brightness observed in Luhman 16B is one of the most pronounced ever seen in a brown dwarf, with changes of over 20% in some cases. Further studies have suggested that Luhman 16B's atmosphere experiences differential rotation, meaning that different parts of the brown dwarf rotate at different speeds. This is similar to the differential rotation observed in gas giants like Jupiter and Saturn, where the equatorial regions rotate faster than the polar regions. The equatorial rotation period of Luhman 16B has been measured at about 5.28 hours, while the mid-latitude regions rotate more slowly. This differential rotation likely contributes to the complex weather patterns observed on the brown dwarf. Recent observations with the James Webb Space Telescope have provided even more detailed information about the atmospheres of Luhman 16A and 16B. These observations detected the presence of water vapor, carbon monoxide, and methane in both brown dwarfs, along with evidence of small silicate grains in the atmosphere of Luhman 16A. The presence of these molecules suggests that both brown dwarfs have complex, layered atmospheres with varying temperatures and pressures. The discovery of these atmospheric features in Luhman 16B has important implications for our understanding of brown dwarfs and their weather systems. The rapid changes in brightness and the presence of patchy clouds suggest that the atmospheres of brown dwarfs are more dynamic than previously thought. This has led to comparisons with the atmospheres of gas giants like Jupiter, where clouds of ammonia and water vapor create bands and storms that change over time. Luhman 16A and 16B orbit each other at a distance of about 3.5 astronomical units, which is roughly equivalent to the average distance between the Sun and the asteroid belt in our solar system. The orbital period of the system is approximately 26.6 years, meaning that it takes about that long for the two brown dwarfs to complete one orbit around each other. The orbit of Luhman 16a and 16b is somewhat eccentric, with an eccentricity of 0.344. An eccentric orbit means that the distance between the two brown dwarfs varies over the course of their orbit, with the closest approach, or periapsis, being shorter than the furthest point, or apoapsis. This eccentricity suggests that the system may have experienced gravitational interactions in the past, either with each other or with another object, that altered their orbits. Astrometric measurements have been crucial in determining the masses and orbital parameters of Luhman 16a and 16b. Astrometry, which involves precisely measuring the positions and motions of stars, has allowed astronomers to track the movement of the two brown dwarfs over time and to calculate their orbits with high precision. These measurements have also been used to search for additional objects in the system, such as planets, by looking for perturbations in the orbits of the brown dwarfs. The proximity of Luhman 16 to Earth makes it an ideal candidate for astrometric studies. The system's high proper motion, about 2.79 arcseconds per year, makes it relatively easy to track its movement across the sky. This high proper motion is a result of the system's closeness to Earth, as nearby objects appear to move more rapidly against the background stars. The discovery of Luhman 16 sparked considerable interest in the possibility of finding exoplanets within this nearby system. Brown dwarfs, despite their low temperatures and faint luminosities, are capable of hosting planetary systems, and their proximity to Earth makes them prime targets for planet searches. In December 2013, astronomers reported possible perturbations in the orbits of Luhman 16a and 16b that suggested the presence of a third body in the system. This potential companion was hypothesized to be a planet with a mass between a few and 30 times that of Jupiter, orbiting one of the brown dwarfs. If confirmed, this would have been the first exoplanet discovered using astrometry, a method that measures the tiny wobbles in a star's position caused by the gravitational pull of an orbiting planet. However, subsequent observations with the Very Large Telescope and the Hubble Space Telescope failed to confirm the existence of this third object. These studies placed stringent limits on the presence of any additional companions in the system, ruling out the existence of any planets with a mass greater than 2 Jupiter masses orbiting within 300 days. Further observations also ruled out the presence of any Neptune-mass planets with orbital periods of 1 to 2 years. Despite these null results, the search for exoplanets around Luhman 16 continues. The system's proximity to Earth makes it an excellent candidate for future observations with more advanced instruments, such as the James Webb Space Telescope and the upcoming Extremely Large Telescope. These telescopes, with their superior sensitivity and resolution, may be able to detect smaller, Earth-sized planets that eluded earlier searches. The search for planets around brown dwarfs like Luhman 16 could help answer fundamental questions about planet formation. Brown dwarfs occupy a unique position between stars and planets, and understanding whether they can host planets and what types of planets they might host could provide new insights into the processes that govern the formation of planetary systems. The discovery and ongoing study of Luhman 16 have significant implications for our understanding of brown dwarfs and the processes that govern their formation and evolution. Brown dwarfs are thought to form in a manner similar to stars, through the gravitational collapse of a cloud of gas and dust. However, because they do not have enough mass to sustain hydrogen fusion, they do not follow the same evolutionary path as stars. The relatively young age of Luhman 16, estimated to be between 400 and 800 million years, means that the brown dwarfs are still cooling and evolving, offering a glimpse into the early stages of brown dwarf evolution. By studying Luhman 16, astronomers can test theoretical models of brown dwarf formation and cooling, and refine our understanding of these objects. The study of Luhman 16 also has broader implications for our understanding of the Milky Way galaxy. Brown dwarfs are thought to be numerous in the galaxy, possibly outnumbering stars, but because they are so faint, they are difficult to detect. The discovery of Luhman 16 suggests that there may be many more brown dwarfs in the solar neighborhood that have yet to be discovered. Understanding the distribution and characteristics of brown dwarfs could provide new insights into the structure and composition of the galaxy. Future research on Luhman 16 will likely focus on several key areas. One area of interest is the continued search for planets within the system. Another area of interest is the detailed study of the atmospheres of Luhman 16A and 16B. Observations with the James Webb Space Telescope and other instruments will allow astronomers to study the composition, temperature, and dynamics of these atmospheres in unprecedented detail. This could provide new insights into the weather patterns and cloud structures of brown dwarfs, and help refine models of brown dwarf atmospheres. Now, what do we know about brown dwarfs in general? These objects, sometimes referred to as substars, are, as already mentioned, characterized by their inability to sustain hydrogen fusion in their cores, a process that is the defining feature of true stars. A substellar object is thus defined by its mass, which is less than the minimum required for hydrogen fusion to occur. This threshold is approximately 0.08 solar masses, or about 80 times the mass of Jupiter. Objects that fall below this mass limit include brown dwarfs and certain former stars that have exhausted their nuclear fuel. Interestingly, the definition of substellar objects can also extend to planetary mass objects, depending on their formation mechanism and whether they are bound to a star. One of the intriguing aspects of substellar objects is that their physical characteristics, particularly their radius, remain relatively constant regardless of their mass. For instance, a substellar object with a mass similar to that of Jupiter, approximately 0.001 solar masses, will have a radius comparable to Jupiter's, even if its mass is significantly higher. This is because, at the upper end of the substellar mass range, the object's core is quite degenerate, meaning that its material is in a highly compressed state. This degeneracy causes the object to have a very high central density, about 1,000 grams per cubic centimeter. As the mass of a substellar object decreases, this degeneracy diminishes, resulting in a lower central density. However, the decrease in density is balanced by the decrease in mass, keeping the object's radius nearly constant. This is why brown dwarfs, which can be up to 75 times the mass of Jupiter, have radii that are similar to that of Jupiter itself. Unlike true stars, substellar objects do not undergo stellar evolution, the sequence of stages that stars pass through as they burn their nuclear fuel. Since they lack the mass required to sustain hydrogen fusion, substellar objects rely on other mechanisms to generate energy. In some cases, a substellar object with a mass just below the hydrogen fusing limit may ignite hydrogen fusion temporarily at its center. However, this process is short-lived and does not provide enough energy to counteract the object's gradual contraction due to gravity. Another potential source of energy for substellar objects is deuterium fusion. Deuterium, or heavy hydrogen, can fuse at lower temperatures than ordinary hydrogen, allowing substellar objects with masses above approximately 0.013 solar masses to sustain deuterium fusion for a time. However, this process is also temporary, typically lasting only between 1 and 100 million years. After deuterium is exhausted, the substellar object gradually cools and shrinks, emitting radiation solely from the release of its gravitational potential energy. As the object cools, its luminosity decreases, and it eventually becomes a very faint, cool body. Isolated substellar objects continue to cool indefinitely, whereas those in orbit around a star can be kept warm by the star's radiation, slowing their cooling process. These objects evolve towards an equilibrium state where they emit as much energy as they receive from their host star. One of the defining characteristics of substellar objects, particularly those in the brown dwarf category, is that they are cool enough to have water vapor in their atmospheres. The presence of water vapor is a key feature that distinguishes brown dwarfs from true stars, as the cooler temperatures allow water to exist in vapor form. This characteristic can be detected through infrared spectroscopy, which can reveal the distinctive absorption lines of water in the atmospheres of substellar objects. Infrared spectroscopy is a powerful tool for studying the atmospheres of brown dwarfs and other substellar objects, as it allows astronomers to detect and analyze the chemical composition of these distant bodies. Even substellar objects that are not in orbit around a star can be studied in this way, providing valuable insights into their atmospheric properties and evolutionary state. The classification of substellar objects has evolved over time, with various systems proposed to categorize these diverse bodies. One of the earliest classification systems was proposed by William Duncan Macmillan in 1918, who suggested dividing substellar objects into 3 categories based on their density and phase state: solid, transitional, and dark, non-stellar, gaseous objects. Solid objects. This category includes smaller terrestrial planets and moons, as well as the Earth itself. These objects are characterized by their solid, rocky surfaces and relatively high densities. Transitional objects. Transitional objects occupy an intermediate position between solid and gaseous bodies. This category includes planets like Uranus and Neptune, as well as mini-Neptunes and super-Earths, which have thick atmospheres but still possess a solid or liquid core. Gaseous objects. This category includes large gas giant planets like Jupiter and Saturn, which are composed primarily of hydrogen and helium and have low densities. Brown dwarfs also fall into this category, as they share many characteristics with gas giants, though they are typically more massive and have more complex atmospheric compositions. In modern astronomy, the classification of substellar objects has become more refined, particularly with the discovery of brown dwarfs and the realization that these objects bridge the gap between planets and stars. Brown dwarfs are typically classified based on their spectral type, with L-type, T-type, and Y-type brown dwarfs representing progressively cooler and less luminous objects. Substellar objects can also exist as companions to stars, forming binary or multiple systems with a primary star. These companions can range from massive planets to brown dwarfs, depending on their mass and formation history. For example, a substellar object with a mass below 13 Jupiter masses is typically classified as a planet, while those with masses above this threshold are considered brown dwarfs. One of the aspects of substellar companions is the diversity of their characteristics and the challenges they pose for classification. Some objects, known as superjupiters, occupy a borderline position between planets and brown dwarfs. These massive planets have masses that place them close to the lower limit for brown dwarfs, yet they are often considered planets due to their formation process and orbital characteristics. The distinction between planets and brown dwarfs is not always clear-cut, as objects as small as 8 Jupiter masses have sometimes been classified as brown dwarfs. This ambiguity highlights the complexity of substellar objects and the need for continued research to better understand their formation, evolution, and classification. While substellar objects may not shine as brightly as stars or play as prominent a role in the cosmic landscape, their sheer numbers suggest that they could outnumber stars in the galaxy. Understanding substellar objects is crucial for building a complete picture of the Milky Way and other galaxies, as they contribute to the overall mass and structure of the universe. The study of substellar objects also has implications for the search for exoplanets and the potential for life beyond Earth. Brown dwarfs, with their complex atmospheres and potential to host planetary systems, are key targets in the search for habitable worlds. While the harsh environments of brown dwarfs may not be conducive to life as we know it, the discovery of water vapor and other molecules in their atmospheres raises intriguing possibilities for the chemistry and conditions that might exist on planets orbiting these objects. As we continue to explore the universe, substellar objects like Luhman 16 will remain a focus of scientific inquiry. Lumen 16 is a system that offers a good opportunity to study brown dwarfs up close. If you are still awake and want more content, go ahead and check out our other episodes. And if you want to help create even more, please consider supporting us. While this manuscript was written by AI and read by me, an AI voice, creating this content still required production time from a human being. If you want to support the production, please make a donation to the Milky Way Traveler over at Patreon. To do so, follow the link in the show notes or search for the Milky Way Traveler at Patreon. If anything is incorrect in this episode, if you are missing some information, or if you just want to add your view, feel free to make a comment in the comment section for this episode. Now thank you for joining this trip, and have a beautiful and wonderful night with sweet dreams once you get there.